Hi, I'm Tim Menzies. I'm from North Carolina State University. I'd like to talk about dodging, complex analytics. This is work with Amrit Agarwal, Wei Fu, Scott Chen, Xiaoping Shen, myself from NC State University. If you want to know more about this talk, have a look at this URL, tiny.cc dodge20. tiny.cc dodge20. All the links are here. What we're after about is configuration. If you take a boring piece of paper, which is useful for many different purposes, if you actually want to use this piece of paper for a particular application, you have to configure it. For example, consider this envelope. It's a folded, it's got some glue, and when it's been configured that way, it can be used for a particular purpose, which in this case is actually to send a letter. Just as with letters and paper, so too with data miners. If we want to have a good data miner configured for the right thing, we have to do hyperparameter optimization, controlling the parameters. Over here, we see examples of how the performance can improve before and after hyperparameter optimization. Bottom left, you see a blue dot above C5.0, and above that there's a red triangle showing the vast delta difference before and after tuning for C5.0. And we see it's actually performing better than anything else. Any conclusion you make without tuning using an off-the-shelf data miner can be overturned after doing tuning. So it's very good practice to do tuning. You get stable conclusions and you get better performance. But the problem is, up here in 2, this is shows some of the parameters you have to tune if you're actually going to do hyperparameter optimization. And there's so many we can't even see them. They're very small on the screen. And if you want to do this number of parameters, which is billions of options, and you want to do it 20 times for statistical validity, and you want to do it for something really slow like deep learning, it gets very computationally expensive, even prohibitively computationally expensive. Well, what to do? Well, let's dodge that complexity using a trick shown up there in 3. Now in 3, we have a learner, and we're running it multiple times, and that's the blue and green curve shown up there in 3. What I've done is I've run it 2 times, each time using 90% of the data. And we see we get similar blue and green curves, but we don't get the same blue and green curves. It turns out that learners are not deterministic devices. Small variations in the data can lead to different models with slightly different properties. Now, if you're comparing multiple learners and you're using this sort of, let's do a cross-val rig to compare them, it turns out there's a degree of wriggle in the performance of any one learner, which means if you're comparing the performance of 2 learners, after some epsilon, it's hard to distinguish one learner from another. So let's talk more about that epsilon over here in 4. This is a 2x2 graph of recall and false alarm. We've assumed that the epsilon after which you cannot distinguish the performance of different outputs is 0.2. And 0.2 dividing up the recall false alarm output curve is 5 by 5, 25 outputs. So please consider, we could either search billions of input parameters that control the hyperparameter optimization, or we could look through 25 output equivalent systems. So what Dodge does is that firstly, it runs any one of these parameters at random and writes down the result. Then it runs any other one at random, and if the second result has the performance within epsilon, say 0.2 or the first one, we mark those 2 results at random. Then we keep picking from this space of parameters, trying to avoid the things that were boring, that were within epsilon of each other. And given an output epsilon of 2, there's only a small number of things you have to pick. After 3 dozen picks, we stop exploring that space of options because this is fast because we're not exploring that large space of options. We're actually doing a taboo search across this much smaller output space. Now it turns out that for defect prediction, effort estimation, GitHub issue close time, bad smell detection, GitHub text mining of issue reports, this epsilon domination approach to exploring hyperparameters works crazy fast, terminates after a few dozen evaluations, and does better than prior state-of-the-art results. And so up here in 6, you can see the number of evaluations required to do things, and the bottom big big blue bar is what happens when genetic algorithms are employed in this, and that's a very large number of evaluations. And the tiny little blue bars showing up above my finger there are what happens when we employ these techniques. So you can dodge the complexity of software analytics. You can achieve the benefits of hyperparameter optimization, even if you're exploring a very large space of options, because the output space of those options divides up into these epsilon cubes of large amounts. So that's our technique. As I say, we're from NC State. Tiny.cc Dodge 20 is where you can find more information about this. Thank you so much for your time. Have a nice day.